Hey guys, how's it going? Sorry for the kind of late start. I had issues getting my dashboard to actually show like viewers in the chat and stuff. But looks like we're rolling now, so that's pretty cool. Although I might have missed some people saying hi, so sorry if I don't say hi back. Yeah, cool. It's good to see you guys again. This Thursday time slot has at least worked out really well for me today, so that's good news. Looks like I'll be able to keep doing this in a pretty chill way, I guess. Yeah. People in the chat talking about how it's really, really cold in Europe right now. And it is. That's about it. Sup, Cries? How's it going? Dana Collin, Ashmadai, Implete, Absconding? I'm not really sure how to say that. How's it going, guys? So, last time, that would have been last Thursday, went over a lot of this Virtual Boy emulator. And if you guys didn't catch my tweet from the other day, I talked a lot last time about moving on to Rustendo this week, but I've got a lot of momentum on this Virtual Boy project, and I think I just want to keep going on it and just keep working because it's getting a lot of stuff done. So much that I'll actually spend a lot of time today just talking about what the process has been like in the last week. Because last week I was still off of work, so I was just basically only doing this, which was super fun. Just made a ton of progress. So first of all, I'll show you a little bit more about the emulator. So this is it running a Japanese version of Panic Bomber. And it runs super smooth. I did a ton of work on, not really a ton of work, a couple evenings worth of work on performance, which was mainly pretty easy. And I'll talk about that later, go over the commits and stuff. But generally, things run pretty smooth. There's a lot of games that basically are fully compatible. This one is, as far as I know, fully compatible. Wario Land is as far as I know, fully compatible. Mario Tennis, which has a cool story behind it. How I finished making that fully compatible. A couple other games, I think. There's still some bugs, and it looks like I've introduced a couple new bugs in some of the games that I kind of want to try and fix today, as well as improving the performance a little bit more because it's still not where I want it. It's using like 5 to 6 CPU on expensive parts and like 2 to 3 on non-expensive parts, but I want it to be in like the 2 to 3% CPU range if possible, generally. And again, there's no audio, but I think last week we worked on the sprites, the objects. At this point, I've also done the affine mode stuff, so you'll see a lot of things are scaled, like these little bombs up here, which are a little bit too small to see right now. I can open up Wario Land so you guys can see that as well. Pull up my thing. Let's see. I also started testing some homebrew ROMs. Found some cool bugs in there as well. Daniel Collins says, do a JIT. I might, because it'd be really fun, but yeah. That basically extends the life of the project by many months. Or at least many weeks. Cries92 says, yeah, performance gets a lot better. I might try compiling to JS again. Last time it was too slow. Yeah, it's like 2 to 3 times faster than it was last week, which is still not saying that much. There's a lot more work to be done there, but it should be at least playable now. Yeah, Osmodai says how to blow up the scope immediately. He also says new about the Virtual Boy. Never think I looked at photos of its hardware. Do you think it was even available in NL? I actually don't think it was. I think it was only released in North America and Japan. It was out for like a year, and then it was pulled. Upsounding says, is there any benefit to emulating the video on a separate thread? No. I mean, maybe a little. But in this case, I did some profiling, which I can show you guys how I did that as well. But the thing is, the video is just not the bottleneck here. It's actually the CPU. The CPU runs at 20 megahertz. And while that still doesn't actually sound like much, if you compare it to like a NES emulator or a Super Nintendo emulator, where you're running in like the 1 to 4 megahertz range, it's actually pretty significant. In fact, the biggest speed gain So I got basically two major speed gains in the last week from this. One is you'll notice the emulator's not printing a ton of debug information. So what I did is I have like basically all the logging goes through a different macro than just like print line or print. It goes through these macros called log line and log. I can show you the code. That's in logging. Yeah, I had a couple comments about how I did this because some of the details about how this one works are a little chunky, but it works. But the idea is that then you have to basically opt in for logging at build time. So this gets rid of a ton of debug printing. So that was like the first major speed up. And then I did a ton of smaller things. Like I went through all of the memory things, like the ROM, for example. And instead of just using these box slices, I was able to circumvent all the bounds checks just by using pointers. So this is a little bit unsafe, but I can basically guarantee that this is correct. The only place I can't necessarily guarantee that this is correct, and I might actually undo it there, is in the video hardware, because I think the way I'm doing a lot of the calculations now, I'm not doing any sanity checks on some of the data. So I think it is actually possible for the video hardware to crash with certain window parameters, just because it'll do like out of bounds accesses and stuff. But generally it's going to be okay. But that actually didn't help that much. I thought it might. Just because there's going to be like so many memory accesses and stuff. That actually didn't really help very much. The thing that did was actually changing instruction decoding. So if we go into the NVC, actually, no, I'll show you how it is now. Basically, actually, let me pull up the code from before, because that'll be a little bit easier to see the actual change that I made. Because it was actually a little bit surprising to me that what was so effective, if that makes sense. Ernest, how's it going? So I'm just pulling up the code on GitHub here. By the way, I'm still getting used to this new microphone, so if I end up like breathing into it and it sounds super weird, just let me know, and I'll try to build a habit not to do that. In particular, it was one of these refactored opcode, decoding, and dispatch. So this was, I think, 2 days ago. Let me pull up the commit before that, and we'll just browse the code here, which I think I can do with that button, but that's fine. Ahmed Isis, we'll just call you Darth Ferris. Maybe that's more like snoring. Oh, also, hey, I made a new logo. I'm not actually sure I'm happy with it, so if someone wants to make a different one, I'll totally consider it. I'm also going to start calling this thing Rustual Boy, because I think that's funny. Although I kind of maybe want a name without Rust in it, but I don't know. I'm pretty proud of using Rust for this right now, so we'll keep it. Also, really quick, shout out to, I think I mentioned them last stream. But it's this planetvb.com site, so I'll link this in the chat here. Move away 00, how's it going? So this Planet Virtual Boy is just an awesome site as far as like hardware preservation goes, and they totally. So I posted about the emulator in the forums, and they totally put a little post on the front page, so that made me pretty happy. So shout outs to them for that. Also, just totally check this site out, because they have the coolest stuff here if you're curious about the Virtual Boy. Ashmadai says, by the way, nice when you have comments that document the why, not the how. How is in the code anyway? Yeah, I totally agree. Like so I mean, there's a little bit of that in the logging thing, just because like, especially this one has a little bit of documenting how here, because like, so what this does to get rid of the logging, the thing is that basically what you need to do is just not like, instead of actually doing print, like here, I'll show you the one that works. Sorry, I'm a little scatterbrained today, but so in the normal like log and log line, it basically just passes everything through to print and print line, right? So that's pretty straightforward. So we have the empty pattern, which just basically prints, yeah. Or is that a single? Oh yeah, no, this is just the format string. That's what that is. And this one's the format string, and then a bunch of args, 0 or more of these. And then that will just do print for all those, and same with like print lines. Basically just passes them through, so nice and easy. The one where it actually doesn't do any logging, so if we don't have the logging feature enabled when we build, basically what we need to do in here is do nothing, But if we just did nothing, we'd get a bunch of compile warnings about dead code. And instead of just allowing dead code everywhere, I'd rather not do that because I think that's a nice compiler check to actually find stuff that actually shouldn't be there. So what we want to do is we actually want to reference all the arguments. We could actually just use them like this, like assign them to a variable with some underscore in the name. The issue with that then is that this will actually take ownership of different things. So we take a reference to that instead. And the idea is that then this will suppress those compiler warnings without, and also be optimized away. So this should basically be transparent. And that's just what these comments are explaining. So I usually don't write comments this long or this many comments, but you know, when it's important, it's important. What I was going to talk about, so we're at this commit here, source NVC. So actually there's basically two major files here that we want to take a look at. We want to look at the NVC and we want to look at the instructions, and I'll zoom in a bit here. Hopefully that's readable enough. But the idea is that in the opcodes thing, I'll actually zoom out a little more to make this easier to see. There's this big enum which basically has all the opcodes, and then there's a big from half word function that basically takes a half word, which is a U16, and then looks at its bits and basically decodes it. So this will decode basically the raw bits into this opcode enum, or value from the opcode enum. And then in NVC, so what we do, and the NVC is the CPU, the main loop here is this step function. And this will basically read the first half word and then get the opcode from that. And then depending on the opcode, it may read another half word and get the rest of the opcode, or whatever it might need. The issue actually is that is basically two indirections per op. So we have this first basically jump table that will decode all the instructions. And then we have a second one that will actually match on that decoded instruction. And it doesn't seem like that would actually be that big of a hit performance-wise. But again, this CPU runs at 20 megahertz, which is, it's 400,000, well, I mean, it's 20 million, max 20 million ops per second, which is about 400,000 per frame. Actually, it's exactly 400,000 per frame. Max, of course, that's if all the instructions take one cycle, which they tend not to, but there are a lot that do. So that is actually pretty significant. So what I did in that change is I still have this opcode thing, this opcode enum, and I still have this from half word thing. But this ends up only being used in the disassembler, where the speed is not that critical. And you'll also notice that all the bit patterns here have been replaced by these big constants up here. And so now the bit decoding logic here, which really is still pretty straightforward. The only difference is that we also have like these panics here. That ends up also being duplicated in the NVC. But because this is so simple, it's only, like a couple shifts and jump table or two. And there were a couple other changes to actually make the code a bit more comfortable. This actually helped quite a bit, so that was really cool. I think that was the biggest, other than removing all the printing, of course, the biggest speed optimization I did in the last week. So that was really helpful. Another small thing I did is I had previously, I can just bring up the code again. Previously, so it would decode the instruction, and then it would actually execute the instruction, and then at the end, after it executes the instruction for this step, then it will actually determine how many cycles that took, basically by, oh wait, that was in an earlier commit. Let me go ahead and check that out here, I believe. Dom170, how's it going? Hopefully I didn't say that twice. Where are we? Refactor instruction cycle counting pattern. So we want to go before that. And if we go into the NVC here, at this point in time, again, this was basically Monday. So it would execute the, whatever instruction it was. And then after that, it would do like a second basically match on that, because it would go into opcode instruction. No, wait, that's not it. Where is it? I know it is here. Yeah, because we have to do special casing for this opcode format. But yeah, it would basically determine the number of cycles again, which would be another match on that opcode struct. One or two of those. So it was basically matching the opcode like 4 different times per op, and that really starts to add up. Especially when you like when you look at some of these ops, especially the ones that were particularly hot when I profiled it, were like move, obviously, because it's actually just moving registers. But I mean, these are just like the simplest things. So when you're doing this and opcode decoding, like it actually ends up being a significant portion of the time spent during per instruction. So that was really important. Just want to kind of go through some other commits that I did and explain some really fun bits of this in the last week. Let me zoom out a little on some of the titles here, just so I can see this a bit better. So I did a lot of stuff. What day was last Thursday? I guess I can look for the one that says 7 days ago. It's the 29th. Is that this day? No, it's a couple days before even. Yeah, because we did object drawing here. I changed some stuff in the README. Did a couple fixes. I implemented a find mode, which is again the stuff that's like scaling. Wario actually has some really good examples of this that should come up quite shortly. Maybe not, depending on whatever level it's at. But again, it's really just like the scaling rotation stuff that some of these sprites will do. That ended up actually being a lot simpler than I thought, because it was basically just like the way that the find stuff is laid out. You have a window into which the thing's gonna that determines an area on screen where pixels in that particular window are going to be drawn. And within that window, you have an offset into the background data, and then you have like delta X and delta Y, which basically determine how that offset moves as you go across and fill in the window. Which that the offsets and the deltas are both expressed in fixed point coordinates, where there is still like a fractional component, but it's all fixed points. So it's basically the same thing. It's just a normal integer, but shifted. So with a couple shifts and some stuff, I can bring that up as well in here. Basically just these 2 lines, other than actually reading the data. It ends up being really straightforward. So that was pretty nice. I also refactored a lot of the drawing stuff. A lot of this was repeated over and over again for like reading a pixel from a character and stuff. And I factored it into a bunch of these small functions, and I inlined all of them as well. So that was another thing that did help performance a bit, because if you go into like basically the innermost function here is this draw char pixel, which will basically read a character and some of its data, and then read a pixel from that character, and then draw the pixel. And there's a lot of calculations in here that shouldn't really be in the innermost loop. They should actually be calculated further up, but if I calculated them further up, then I would have to pass just a ton of arguments. I'm already passing quite a lot to this function. But if we inline this, then the compiler can actually take these and start lifting them out of loops, which it seems to do quite well. I haven't actually checked the disassembly of this part, but I noticed a noticeable speed improvement. But at this point, like sitting here optimizing the drawing hasn't done that much good for the emulator, because like I even disabled the drawing and it's still about as fast as it normally is. Like it takes 1, maybe 2 milliseconds to actually do the drawing for both screens on my PC. And I have a pretty beefy PC, but still, that's just not where the gains are going to be right now. And normally I wouldn't care that much about performance this early anyway, but I mean, the emulators actually come pretty far, so kind of the time to start thinking about that. Although there is, of course, more to do. Let's see, what other stuff did I do? Yeah, that was the drawing function stuff. A lot of refactoring on that. So, so already here, I'm getting into watch points here. I thought I did that a little later, actually. Let me just look at what I did. I just did so much in the last couple weeks that like I just don't remember exactly what I did. Anyway, watch points are basically like breakpoints in the debugger, but instead of breaking when the code is going to execute like a certain instruction or from a certain address, you break into the debugger like when a certain memory address is accessed. So for example, I can actually show this. If I hit F12, I'll break into the debugger. And so now over here, let me resize my windows a little bit. Zoop. Ratchet2497, how's it going? So here you can see we have a little console here in the debugger, which I believe I showed this last week. We can, for example, add a watch point at F.014, I think, is the display status, or the drawing status, I mean. And now if we continue, we didn't actually get that far. You can see it, the address here did actually change, so we did actually hit some other instructions. Yeah. So anyway, we're able to break. This is actually the instruction after the thing that accessed it. So we'd have to like disassemble and kind of move around a bit to actually find the instruction that accessed this in particular. Anyway, that's really useful. Had to use that for some debugging that I'll get to in a second. Excuse me. Rats2497, doing pretty good. How about you? I'm not doing too bad. Not doing too bad. Liking the new time slot. Pretty happy about that. Making a lot of progress on this emulator, which is really, really cool. Yeah, I also started implementing floating point stuff. And it was really funny because basically one of the reasons I've been putting off the floating point stuff in the CPU, it's actually not very complicated. There's only like 6 instructions or something that actually deal with floating point. And it's like add and multiply and convert to and from short and stuff. But I actually made a really funny mistake that made Galactic Pinball break in kind of a funny way. So what I want to do is actually recreate that bug and then show you. So I'll pull down my code here. Just because I thought it was super charming. There's been a lot of these kind of bugs in doing this emulator, and I think it's a really cool part of the process, so I want to try and share some of these. I'll do the same thing when I get to the Mario Tennis bug in a minute. Just finding the op down here. If I remember which one it is. Which is this one. So it'll take a minute to build. I think the compile times got a little bit worse than the last week as well. But this is one of the games, as far as I know, is fully compatible as well. Cool. So I can basically get into the game and I hope this breaks the way that I think it will. And this is basically playable. We'll hold A, and now we can launch the puck. And the puck just goes to the left. I don't know if you saw this. But I thought that was just super funny. It's like I implemented all these operators, and then like something was wrong, and that it manifested in the puck just going to the left. I think that's super funny. Anyway, the mistake I made is pretty great. My cursor was on it, so you probably just saw it. But so the basic floating point ops is there's some extra decoding, but they're really simple. It's just like here's compare two floats. We just subtract one from the other, and we set some flags based on that. There's convert word to short, convert short to word, or single, I think is what the S is. The single is for F32. And so what I actually did is I implemented add, and then I implemented sub, and then I implemented multiply, and then I implemented div. And there are maybe a couple others, and then the game actually started to work, but of course I had that problem. And if you can see it, it's pretty funny. But the idea was that I copied and pasted this add function over and over again. And the one thing that I forgot was to change this sign here in the sub instruction to actually be a subtraction. So that was all it was. So I'm guessing it was the, like this didn't take long to debug because I just like read through this code and was like, oh, nice. But it's really easy to make these kind of mistakes, so I thought that was pretty funny. Yeah, Moraxa says, hi, why is the emulator output an N glyph? Yeah, it's because it's a Virtual Boy, which has 2 separate screens. So that's what I'm doing there. So yeah, so fixing that fixes the game. So that was a pretty easy glitch to fix, but I just thought that was super charming. There were a couple, actually, before I fix this, I want to show you a couple of the other bugs that came with that. I just thought it was super funny. There was V Tetris, I think was one of the games that bugged with this. It's just funny the kind of art, like the kind of way these bugs manifest themselves, like the puck just going to the left, or this one is particularly good as well. There's these particles in one of the title screens. Should be coming up here, and all the particles just go to the right, just to the bottom right. And I don't remember if any of the games actually broke really hard with this, because I think I had to implement a bunch of other stuff before many other games would run in this case. But yeah, they just they just go to the right. So that's kind of funny. Super easy to fix. And that will fix both problems. So that was one of the things that I did. That was a sub FS bug. Another couple things, there were rounding errors. So actually, I do also want to share some more of these bugs, because these are pretty good ones. I think we're running that now. Just show you that it works. This is not a very good game, by the way. Like you're gonna make a next gen. You're gonna make a game for Nintendo's next gen 3D virtual reality console, and you make Tetris. So that's cool. Anyway, now they work. Break this again, because I think. Oh, sorry, it wasn't that bug. It was a different bug. I initially had the rounding when it was doing converting to from and to words into singles, and initially I was rounding towards 0, which is what this does, and it had a funny bug in Mario's Tennis. And again, I just had a really fun time trying to debug this stuff. Just playing a lot of these games. It was the first time they were actually able to run at all, and they had just these stupid bugs. So this is the normal cutscene when hits the ball at your face, and you'll notice the ball and also the logo are just like slightly to the left. And I haven't actually looked at the code that places these, just because like I noticed there was a lot of float stuff wrong, and I just went and looked at the code and then fixed that bug. This rounding error. My guess is that they were doing, in order to figure out the placement of the ball and the logo for those parts, they were doing like convert some word into a single, and then actually move it, and then convert back and store it. So every frame you'd get a little bit of that rounding error accumulated, and I'm pretty sure that's why that logo just ended up to the left. I thought that was pretty great. So that was another thing. Hold on, let me see what okay, we're fine. That was another thing we did. Just did a couple fixes. I did save RAM persistence. So if I open up like Wario, my save games are there. Kind of show you that, which is really, really trivial. Although all the save RAM files in my case are like 16 megs. So I think I'm doing that wrong, because I'm trying to just use as much memory as the games will actually access. I'm not really sure I've done that correctly. It's probably because I've initialized all the memory to FFs, and I think the games will actually try and clear that. Or something, not actually sure. But they all end up being that size. I should probably just save like exactly how high it goes, instead of trying to do powers of 2, but powers of 2 have other benefits. Okay, so I guess I didn't have very exciting save games in that one. I think Teleroboxer as well. I don't know if you're supposed to pronounce it Teleroboxer or Teleroboxer. I tend to say both. So here, I really like the opening to this game. This little cutscene. This was another thing that didn't work last week. Mostly because of the floating point stuff. Like I think it could get through this screen. Also, maybe it's not this one. I'll get to that in a sec. But I actually implemented a hardware bug on purpose because it's a bug that's supposed to be there. So yeah, you'll notice the fists on the little boxer there can actually scale properly now. Same with that logo. Yeah, so here we go. Here's an actual save game where I believe I beat the first guy. I'll go fight someone else. So that was something I did. And I think, yeah. So January 1st, yeah, this was New Year's. There's just a ton of stuff about like just cleaning up some logic. Let me show you. I'll again trigger a bug. So this is the Mario Tennis bug. If you guys follow me on Twitter, you'll have seen that I posted a picture of a really broken Mario Tennis game. And I'll trigger this bug so I can show you what happened, because I think it's kind of cool how I ended up fixing this. Or first of all, how I figured out what the problem was, because that took like 6 or 7 hours. And then I fixed it really quickly, but that fix actually broke some other games. And then I spent many more hours trying to figure out why that was. And I ended up finding the answer. I cheated a little bit. I looked at another emulator called Mednafen, just to be sure, like to just, because I was really running out of options at that point. And it turns out that there was a little trick in there that by the time I get a proper flashcard, I can actually test myself. But until then, I just kind of have to trust that it was correct, because it did actually fix the problem. But first, let me re-trigger this bug. And now I'll show you what this looks like. So you saw earlier Mario's Tennis was running just fine. And even now, it will do this first screen perfectly fine. No problems yet. You can see the logo's in the middle again. So if you go into the next screen, you'll notice the background looks a little messed up. So let's go back. And now you'll notice that there's quite a lot of graphical corruption. So anyone up for some 10 blue? So that's just what the game looked like. And you can kind of go back and forth between these screens. And you'll notice the corruption is slightly different every time. But regardless, it's pretty broken. And so the weird thing about this bug, Miraxis, this game looks fine to me. And it's fully playable. So that's one of the interesting things, is that like it doesn't seem to affect the game logic at all. Like you can totally play this. In fact, a lot of these screens will work. But like if you start playing, maybe it won't happen, but maybe it will. It's a little bit intermittent. But the idea is, here, I think I might have to restart it to actually go in the game. But you'll get like a few of the frames of like the walking animation will be messed up. So just like here and there, it'll be pretty bad. So my basically the only clue is that like all the other games around that time were working fine. So it wasn't likely to be, well, by that logic, it wasn't likely to be a bug in like anything, but clearly something was wrong. So I basically didn't know where to look, because like I've only been working on this emulator for, well, actually almost a month now, but still like there's bound to be a couple bugs somewhere. Like there's a couple games like Vertical Force and Space Invaders where the like lasers won't show up, or enemies are moving in like a sine wave, and like half the sine cycle they just disappear. There's a couple games that, as far as I know, softlock. Or actually, no, that's also Vertical Force that softlocks on the first boss. So it's like little bugs like that. I'm still not sure what those are, but it was weird that this game was working so well except for the graphics. So I kind of just had to dig in. So let me rebuild it with the logging to try and recreate. Yeah. Try and recreate what happened here. What is up with my console here? So I have to pull up the logging build because, yeah, lots of text. I know that's just going to destroy the Twitch encoder, so I'm going to pull that off screen actually. And what I'm going to do is like the thing about this logging stuff is you kind of get used to the shape of it and what it looks like. And when stuff goes wrong or like it accesses a bunch of registers that like aren't implemented or some addresses that look weird, there ends up being just like a big block, and you can kind of just see it rush by. I'm not going to attempt to show you, unfortunately, just because it's, yeah, I really don't think it'll come through in the stream. But I can make it happen, and then I'll show you what it looks like. Let me... Okay. So it totally just happened. So there's a lot of this stuff that just looks like the same kind of things over and over again. So I guess this kind of emulates the thing. And at some point up here, we get attempted read byte from unrecognized VIP address. VIP is the video hardware. Get a bunch of these just reads from weird addresses. And like that was basically the only clue that I had, was that it was doing a bunch of these reads. Now, it was a good thing that I had implemented watch points, because I basically set a watch point on one of these instructions. Let me pull up some of the notes I made when I was doing this. Jacob Mishka, how's it going? He says, welcome back to Twitch. Thanks, man. Just going to pull up some of my notes. Actually, maybe I can see if this will do it, because I'm not... There's like specific addresses where sometimes it accesses and sometimes it doesn't. But the idea is that I was able to set a watch point in here. We can just pick one and see if it works out. So I'm going to add a watch point to one of these weird addresses. I'm just going to continue execution. I'll pull this back down so it won't ruin the stream. And we'll just continue. And it's fine that like we're in a different screen and stuff, because it'll still trigger. Yep, there it triggered. Let me do it again though, so I can pause earlier. Okay, so actually that time we just hit the watch. You'll notice the screen is black. So here, whoops, I continued. Hold on. Just gonna sit here and go between screens until it happens again. Until we actually trigger that. And it may be a little finicky just because it does slightly different addresses every time. I might have to actually set a different one as well. There it goes. Looks like we just hit it. So yeah, so here's a bunch of reads from these weird addresses, and then we break on this instruction, right? So from here, we know that we're in the code that's at least doing some weird stuff. We don't know necessarily that this is the code that is causing the glitch, although there is evidence to suggest that this basically only happens, like whenever the graphics are corrupted, how do I want to say this? Whenever this happens, there's corrupted graphics. Not necessarily the other way around. Like sometimes there's corrupted graphics without this happening, but always whenever this happened, there was corrupted graphics, right? So that was kind of the big clue. Again, it still might not be related to this, because there's a couple games that like read from like the cartridge expansion port and stuff that just like, there's nothing there in the commercial game or whatever, but it's like it still reads it, but it works fine on the system. So you just kind of have to let it slide. And this may be one of those cases. But this is just where I started digging. So we can probably remove this watch, by the way. And what we can do is we can start disassembling. So I can like disassemble the next 20 instructions. And basically what I looked for next was like, what else is this code doing? Like if we step through a few instructions, do we get another read from a weird address? Yes, we do. So that's definitely, we're in that loop somewhere. And you just sit here and disassemble instructions until you like find certain things. Like for example, one of the things that stands out here is this jump to the address at register 31. This is basically how you return from functions in this architecture. If you guys are familiar with like MIPS, it's very similar. I think, does ARM do a link register like this, or do they have a stack? I don't know. But anyway, so this kind of indicates that it's like an end of a function. And so what I'm trying to do, or what I was trying to do here, was like basically go back and forth disassembling stuff until I found like any kind of clue, like that this was a certain function that was being called somewhere. In fact, I think I can set a breakpoint here at this address. If I add a breakpoint there and continue. There we hit it. So there's a bunch more reads. Then we hit this. I can step. And now if I disassemble, you can see that this was right after, and like we just returned from the function. So this is the instruction after. And I'll save you a little time and just tell you that these, I think this 5C here is actually the function that it was at. So I just like sat there disassembling and like tried to set a breakpoint at the beginning and at the end of the function just to see if that was always where this was occurring. And I ended up finding it. Let me try to pull up some of my notes. Because I started making a lot of notes for this. Yeah, so it is this F58135C is the address. So I can actually go there and show you some of the disassembly. So this debugger, I'm still just so happy with this. Not because it's a great debugger, but because it's one of those tools where it's like, it has enough features to be really useful, and I didn't spend that much time on it, so I'm really happy about it. Anyway, if we look at some of the stuff in this function, it's going to add some stuff to this R3 register, which is basically going to, like this ends up being sign extended, so this is actually subtracting 8 from R3, I think, so it's creating a little bit of stack space, which it will use later below. And then it will do a bunch of stuff and eventually return. I don't think the function is terribly long. It felt long by the time I had reverse engineered all of it. Yeah, there goes the F4 here, I think was the end of the thing. No, that's wrong. 1496 is what I have in my notes. Yeah, that's actually here. Yeah, 1494, so that's for the end of the function. So I was looking at that, like that's one thing. The other thing that I found was, so that was like the whole function. In order to start reverse engineering some of that, I needed to know what like things like the arguments were. So I also ended up digging from, like you saw, we had the call site because we returned from the function. I found out where that function starts. So as you can see, it loads some registers and then calls this function, loads some registers, calls another function, loads some registers, calls this function again. So it calls it a couple times when it's changing screens. That's the other thing that I noticed. Is I ended up setting a breakpoint here and only noticed that this function that we're in now was called when it's trying to change screens. So we know that some function is called a few times when we're changing screens, and that function ends up maybe corrupting graphics, but definitely looks related. We also know where the function is and how big it is just from poking around. And that's kind of a long process, but I mean, you can do it. And what I ended up doing, let me pull up some more notes. If I hope I still have this saved. Yes, I do. So what I did is just from this big disassembly dump, I just copied it over to my text editor. So I had all this assembler. So there's about 120 lines, which is sizable enough. It's enough to take a while to get through, but it's not terribly much. So it's like, okay, if I'm going to understand this, I kind of have to just hand decompile this, right? To actually understand what's going on. Let me see if I can find some notes that was like halfway between those, because I don't want to do it again. I ended up doing it twice as well because I messed up the first time with one of the registers. I'm still not that used to reading this kind of assembler. I can show you some of the other notes I made. So for example, from looking at the call site, you can actually look at, this is the call site we had. So again, these are just the notes I made while doing this. And it, like we saw earlier, the call site actually called this function a couple times, which we saw, where was this? Was it this last chunk? Yeah, of course it is. Sets some registers, calls this, sets register, calls something else, sets register, calls this again. We knew that this is the routine that was doing the weird writes. So I was just looking at the registers here. It sets up R6, R7, and R8, and you'll notice it does so in reverse order. That right there is a dead giveaway that these are function arguments, especially because the pattern here, like it does this before it calls any of these. And of course, if we cross-reference some of our documentation, for example, that sacred text scroll document, which I mentioned last time, which is available on PlanetVB, and also some other documentation that I've seen as well. Basically, it gives a little bit of information about what the C compiler is doing and what different registers it's using. Let me try and find this in the document. I'll pull this over here. Just try this. Here we go. Yeah, calling convention. Let me link this. Probably won't link to the right section, but you can search calling convention in there. I know this is going to be a bit small, but it's like gives you what the different registers are for, right? So like R31 is our link register. R3 is our stack pointer. That's where I found that out. R6 through R9 are reserved for function arguments. R6 receives the first argument. R9 receives the fourth argument. So that's pretty cool. Yeah, so that's basically exactly what we're seeing here. We're seeing R6, R7, and R8 as function arguments. Now, in reverse engineering some of that, I noticed have it in this notes, but basically R8 is never used. So R6 and R7 are different inputs. And if you look at the addresses here, assuming that this might be something like, we know that this was doing some weird reads in video memory. And those weird reads, if we look at them, look at kind of where they are, they're around 7-7 with 3 zeros after it, right? If we look at this, you can see there's 7-8 with 3 zeros, so that's pretty close. This one's a little farther, but I ended up disassembling the first call. So if we look at R6, I have a note, this is the one that's meh. So if you look at R6, this is this address, and I did a mem dump at that address, which you can see down here, but I just want to show you in the debugger, give you the authentic experience. So this memory command just prints 256 bytes starting at where this is. Now this is in ROM, and these are the bytes we get. And if we look at a little bit of the code in this routine, that was up here. The first thing it does is it adds 2 to R6, right? Now that may not seem significant, but the first thing we see in the beginning of this data is that it starts with 2 zeros. So what we can kind of guess is that this is correlated, right? And it turns out that I also broke into some other invocations of this function and found out that that was always the same pattern. The first 2 bytes of these chunks were always 0. So at this point, you're kind of thinking like, okay, this is probably a routine that's moving graphics, probably moving it from ROM into video memory, because that's where this stuff ends up being. In fact, I believe this is in character memory. I could be definitely wrong about that though, off the top of my head. So it's still a bit strange that this register was never used, but we can basically ignore it. And from looking at the next little bits of these, because there's also this other pattern where it would load bytes from R6 into registers, and then it'll increment R6. So this is basically like reading bytes and then incrementing that data pointer. So through this kind of process, I started making different versions of these notes. So like this one, I tried to kind of put this in more C-like syntax or more Rust-like syntax. And the reason I did that is because one of the things about this assembler format is that its data flow is left to right. So this is load byte from R6 with an offset of 0, like 0 plus the value of R6 into R10. Whereas most of the assembler that I'm used to reading, like x86, 6502, Z80, all that stuff, kind of goes right to left. So this generally was hard for me to read. So I was trying to put it in a format that was a little easier for me to read and then trying to figure out some stuff from it. Of course, what ended up happening is I got some register names wrong in here, so I had to do it again. But the second time went a lot faster because I was a little more familiar. But so I would do that, and then I would look for different kind of patterns. Like one of the patterns that I would see all the time is it would do, let me see if I can find one of these. Yeah, here. So it's going to like shift left a register by 16 bits and then shift right with sign extend by 16 bits. And like, so this basically means you're going to chop off the top 16 bits and then shift it back with a sign extend. So you're going to sign extend the 16-bit number. Like that to me is a clear indication that whatever value is in R13 at this time is going to be a signed 16-bit value. So there's a lot of stuff like that in here where I could start finding patterns. You can see that I also outlined a couple addresses in here. That was when I was figuring out like, these are basically, I was marking addresses where things would either jump to. I think that's actually all it was things would either jump to or branch to these different addresses. So I just kept looking at that, and I started noticing a couple patterns. I would also mark out like whenever it would do. So here we could see if I can see one of these here. So it would always load bytes from R6 and store bytes for R7. Okay, so it's definitely moving data from R6 to R7. So we can basically conclude that those are our source and destination registers. Let me try and find my last bit of notes where I actually started making sense of all this. Here. Oh, nope, that's not the one I want to show yet. Was it this one? Yeah. So I started making other notes, like just looking at this stuff. Like here, I actually started like rewriting it in kind of a Rust-like format. I think this one's actually wrong. But we could basically tell that like these were the source and dest for these, and I could figure out which registers they were in. I also found some different local things, and it looked like, yeah, I found these things that looked like what I called control bits, and those were just like, it would always read a byte before it would start in another loop where it would loop through the bits of that byte and then do different things based on that. So I just called those control bits before I knew what they were. Basically, though, long story short, because I don't want to sit here for like 6 hours trying to explain all this, I ended up, which one is this in? I can actually just pull up the gist because I ended up putting it in a GitHub gist. So I ended up totally reverse engineering this this routine. And what I'm left with is basically an LZ77 based decoder. So it always skips the first 2 bytes. It preserves the destination, which it needs for some other things later on. It's going to load basically an amount of bytes that like is the uncompressed size of this data. Then it's going to just loop until it runs out of, like, until it's decompressed that many bytes. You'll notice also some of these data types are I32s, and I mentioned, of course, that a lot of these were probably like I16s, but it turned out that in the algorithm it didn't seem to really matter, so I just kind of removed that to remove visual noise. But yeah, so then I figured out that the bits that it was looping through are actually like packet flags. So if you guys are familiar with LZ77, it's basically like, it's a really simple format. You have little packets, right? And each packet will either start with a 0 or a 1. It doesn't really matter. Like, these details are encoding details, but like, say it starts with a 0 bit, then the next 8 bits are going to be a literal byte that goes straight to your output. Where if it's a 1, it's going to be like, it's going to have a distance and length pair, and what it's like after that 1 bit, and the distance is going to decode how far back from your current position to look in the already decoded stream to start finding like a match for certain data, and then a length, and it basically just copies those bytes from the stuff that's already been encoded to where your current data pointer is. And sorry if that's kind of a confusing explanation, but the idea is that it's basically just like either writing literal bytes or copying different runs of bytes from what it's already decoded. So just like trying to find patterns in the data. So this was encoded in a way that instead of doing like having a 0, 1 bit and then the next part of that little string, it would pack all the like 0, 1 bits for 8 different packets. So either 8 different literal bytes or 8 different runs or a mix of those into 1 byte. So it would read the like packet headers in 1 byte, and then it will use those 8 bits as headers for the next like packets that it processes. So that's why I call those packet flags here. And then it will iterate over this. This also still says control bits, even though that should say packet flags. And so for each one of those, we load a data byte first, and depending on whatever the packet flag was, we'll determine what that byte was for. So in this case, if the bit was a 1, that was a literal byte, so we would output that. Otherwise, we would do some bit shifting with that, and then read another byte as well and shift that in there to find the distance to look back. There was some other bits in that data byte would also be the length of that run. And then there's some other details there that aren't terribly important, but then it will actually just copy those. And that's basically it. Then it would shift the bits out of there, and it will try and break the routine if there are no bytes left. Now, the reason why this is cool is because after doing this twice, I was able to like reverse engineer quite accurately a working algorithm that I could recognize. You know what I mean? And the reason why this was really good is because I wasn't sure going in, like seeing this bug, if it was a problem in the video hardware, if it was a problem in the CPU. I didn't really know. And so I was just trying to remove variables. And this removed actually a lot of variables because it removed like, it probably wasn't the instruction decoding because I was able to figure out, a working algorithm with this. so that was really big. And it also gave me like a list of all the instructions and registers that are touched in that algorithm. So I could go, one by one in all the different instructions and check the code and make sure that was correct. And so you'll see in my commit history here, there's a ton of stuff where it's like, I'll zero extend for something, or I'll put parens something, and just like these little clarifications just to make sure that this was correct. None of this had any bearing on the actual like functionality. Like none of this actually fixed anything. But I mean, it's just about removing variables because you just don't know what the problem is. The other thing that's kind of cool about this is now I have this routine, right? And so the next thing I did is I said, okay, now that I have this routine, is reading those weird addresses part of normal operation or not, right? Because I still didn't actually know that for sure. I could pretty much assume that, but I didn't know it for sure. So what I did is, let me find the code here. Since the thing was already Rust, pretty much, I made another project here where I actually made it proper Rust. And so here's the same thing, but it's Rust code now. And it also doesn't actually use source and destination as pointers, it just has a data buffer. And I actually don't think it ever actually writes to this. What I do is I have these read byte and write byte functions. And I basically, in those, I just log stuff. I log all the reads and I log all the writes. And from there, what I saw, let me put this back. So this, by the way, is also using that same data from that ROM, at like the same offset, which is this offset. Exactly the same parameters that it was giving the assembly version of this as well. So if I run this, let me run that. Oops. Oops, I'm in the debugger still. So that was all the output, right? And looking at this, it's kind of hard to see, but when there were, more on my screen, when my pixel density was a little higher, or my font size was a little lower, that is, you could actually start seeing patterns. In particular, I think I had the writes commented out, and the reason why I did that is because you can kind of see where it's reading from. And first of all, you'll notice none of those weird addresses are in here. And you'll also notice it's basically, it'll read a couple times from ROM, and then it'll read a few times in these sequential addresses from the RAM near where it's writing to. Always at addresses after the initial address, never before like the weird writes we saw. So a couple of things about this. First of all, this looks like really healthy memory access patterns for an algorithm like this, because it's basically only reading from sequential accesses or sequential addresses in ROM, and then sometimes it's reading from sequential addresses in the RAM, but not all the time, right? So these would have been a lot of literals in a row, and then these would have been a couple runs of back references. So again, now we're like totally convinced that this is totally a decompression routine. We understand the decompression routine, and we know that those weird byte accesses are not part of its normal operation. So this is a lot of progress, right? Now we know that we need to find out why it's reading at those weird addresses, right? So something is not executing correctly. So I think this is actually the point where I went through and like all the different instructions and made sure those were correct. I hope I didn't give it away by showing you the commits, but anyway. So I went looking through all those instructions, basically found nothing other than some clarifications that I made, but again, it didn't fix anything. And I was kind of frustrated at that point because I didn't really know where to look next. But what I did is I started just running it a couple more times. I didn't want to just sit there and step through the code because I knew that this was kind of a big data set, and I thought that would take quite a while to actually do because it's, not the most straightforward code to follow, even though I had done it in the disassembly. But what I did is I just started like setting breakpoints in other places, in particular the interrupt handlers. Like the frame interrupt as well, because I wanted to especially see like, is it still running frames at this time? Is the timer going off at this time? Like I just didn't know. And one of the things I noticed, let me run this game again and trigger the bug again, and I'll show you something that I should have noticed at the very beginning. So I'm just going to trigger the bug again. So there it happened, but I didn't catch it. There. So let me scroll up again until I can find where we had all those weird reads. Okay, so here's a big chunk of them. And if you look at the top of this, you'll notice something interesting. You'll notice that first a couple of things happen. One of the things that always happens before this is it will write to the drawing control and the display control registers, and it will basically write these bits. And these bits effectively just mean disable the display and also reset them, and same for the drawing. And then it'll touch a couple other things. Nothing too exciting. But then it'll start doing these weird reads, and always, every time it does these weird reads, this is what I should have noticed at the beginning, it's right after it returns from one of these exceptions or one of these interrupts, because they're the same from the CPU's perspective. So at this Fe40 exception, every time this gets corrupted, that's always right after one of these. Now Fe40 is the frame interrupt, basically. It's actually the video hardware interrupt in particular, but this one, just because of the way the registers are set up, this was the beginning of the frame, or beginning of display processing, I believe it is. So if we go to that address, that will break on Fe40, just like the name of it, and we disassemble stuff. Yeah, the first things it'll do is, like, the interrupt only has like 16 bytes with which to actually do anything. So basically all it always does is just load some register with an address and then jumps there. So if we can step through that little bit. Whoops, I need to actually add a breakpoint there. There we go. We'll step through there, and then we can disassemble. And now we're at this interrupt handler. Now, because interrupt handlers interrupt other code, what they always end up doing is they always save a bunch of registers, go and do something, and then restore a bunch of registers. And the idea is that way, when code executes from where it was before the interrupt fired, that it will actually preserve those registers. However, the problem here is that there are many registers that aren't in this list of ones that it was trying to preserve. In particular, there's, I think, is R11, R12, R15, and R17 were ones that, of course, I was quite familiar with now by the time I had disassembled this many times. And I thought, okay, maybe this interrupt is actually clobbering the registers. So to test that, what I ended up doing was I set a breakpoint at the beginning of the decompression routine. I set a breakpoint at the end of it. And I did this like when I knew this would fire. So I put it at the beginning of the graphics routine, at the end, and so that way when I went to go change screens, it would trigger the breakpoint. And then at that point, I set another breakpoint at the beginning of this routine, at the end of this handler, right? So I set one basically here and here. And what I did is I just like stepped those four, and every time I would do that, I would just print out the registers. And I would notice, of course, that especially R12 and I think a couple others suddenly had a bunch of these extra bits tacked onto the front of them. And it turns out that was totally the problem, was that this interrupt was actually clobbering the registers. Now, assuming this was the case, I figured it probably wasn't the interrupt handler's fault, because like we have basically verified that there's a ton of stuff that's working correctly in the CPU. So that basically clearly wasn't the problem. The problem, of course, is that this interrupt basically triggers when it shouldn't have. So something that the CPU was doing, in particular, disabling and resetting the display, meant that interrupt actually shouldn't have fired, whereas I was firing that interrupt anyway, right? So, pretty long-winded, and at that point, I was very tired. Way to bring in the new year. Now, this is actually pretty fun. So this, let me go into the VIP, show you how I fix this. So in particular, that interrupt was here. There's a frame clock, which happens basically every 50 times a second, every 20 milliseconds. So this frame clock happens, and if the start of display frame interrupt is enabled, then we're going to actually raise the interrupt. And this is actually the thing that was breaking it. And the way I found that out, of course, is I basically, like, I knew that video hardware interrupt was firing, and that's what was breaking this stuff, but I didn't know which interrupt in particular was breaking things, so I just commented out a bunch of these until one of them actually fixed the code, and that was this one. So naturally, I thought, well, this happens at the start of the display frame, which is when the video hardware is basically two major components. There's a display piece and then a drawing piece, which is actually really similar to a GPU, where you have one piece of hardware that's basically just pumping pixels out of VRAM into whatever display hardware there is. In this case, the LED screens, and then the other one that's actually drawing into VRAM, and it's double buffered as well. So I thought, well, if the display is not enabled, it's probably logical not to fire this register. So the fix for all of this was that. And that ends up fixing the problem. So that was pretty simple, and it was pretty logical. And I ended up finding some information. I think it was when I dug into Metnofen later, which was a while after this. I hadn't dug into that code yet. The next part that broke, which is what I'll explain in a second, is after that, it's where I dug in. But I ended up finding that was correct in that emulator as well. So that's at least, like, I figured it out logically and verified it in another emulator. It's probably how that actually works. So that was, it took me quite a while. Let me actually read the comments now. Moveaway00 said, man, missed a bunch. I don't think he missed that much. I mean, I think I'm probably talking a bit fast. I tend to do that. Jacob Mishka is saying you moved on from Emacs. Not really, just I'm on Windows. Thrasher HT says, oh, you're on Windows now, any particular reason? And the reason is because I actually built a desktop. So I moved more or less permanently back to Norway rather than traveling back and forth a lot like I was doing before. So then that's basically why I was on a laptop all the time. And I thought I'd build myself a desktop for the first time in many years. Did that, and that runs Windows. So that's why I'm on Windows. And then my Emacs stuff was kind of annoying to set up, actually do cross-platform key bindings with some of the key bindings I had set up, so I just used Sublime. Anyway, so that was, I mean, it was kind of a cool process because, again, like I verified a lot of stuff. I felt really good about the CPU implementation, for example, after this. And it's always fun to like reverse engineer this kind of stuff for an architecture you're not that familiar with. So that, I mean, all in all, it was pretty cool. But the problem was it fixed this game, but it broke a different game. In fact, it broke a game called Space Squash. And the way it breaks, I don't even have to show you because it basically just doesn't show anything. It just sits there, waiting for an interrupt actually. And yeah, it turns out I did a little bit of disassembly there, not nearly as much. But I was just looking at the different bits that it was writing to the different control registers, and basically it was waiting for this same interrupt without ever enabling the display, right? And so that's a direct contradiction to what this game requires. So I was pretty sure this was correct, so it probably had to be something else, but I wasn't really sure what else it could have been. So I sat there for many hours trying like different combinations of changing the timing. I tried to say like, okay, well, the Mario game will disable the display. Maybe it's not that the display enable is what actually stops the interrupt, but maybe it's like a reset period that the display has that might actually be causing it to not raise the interrupt during that time. But I had it up to like, you know, multiple milliseconds, like 10, 20 milliseconds of doing this, which is like half a frame. And that's just like a huge amount of time when we're talking about a 20 megahertz system where it was doing like the reset and it would still corrupt graphics. So it definitely wasn't that. And the thing I ended up finding, because again, I sat here and just messed with this for hours. And the thing I ended up finding is that actually on startup, and this is a direct contradiction to basically all the documentation I've seen, the display hardware is actually enabled by default. And this is the thing I found at Metnofen. I basically looked at their video hardware code, and a lot of it was really similar to mine, which is good because that means a lot of this is at least sensible. But yeah, this one display enable thing was actually true instead of false. Now, I'm not actually sure. I need to do some hardware tests to actually verify this, but it does fix the problem. It does fix the problem in the other game as well. And it could actually make sense. A lot of registers are basically undefined at startup. This one is supposed to be one of the ones that is defined, and it's supposed to be false according to a lot of documentation, including one particular source that should definitely be correct. But it is possible that this is actually the case, because you still wouldn't get a picture on the LEDs on startup until you enable these sync signals. And there's a couple other things you have to do as well, as like setting the LED brightnesses, which I actually believe those are undefined. But especially the sync signal thing actually enables signals from the display hardware to the video chip that will actually, that's how it actually knows when it should start sending pixel data to LEDs. So if this is not enabled, like if this is the startup state where the display is enabled but the sync signals are not enabled, it's actually quite possible that that this is the correct startup state, because you still wouldn't get anything on the screen. Again, I would need some hardware to properly test this, but this does actually fix the problem, so that was fairly interesting. I wrote a not very happy commit comment about that, because that was not very fun. So I think both of those things were in the same commit. Yeah, here. This was a bit crap, is how it opens. And then just explaining what I just explained. Anyway, that was actually super fun. DevPram, how's it going, man? By the way, guys, if you haven't checked out DevPram stuff, just got a quick 2 minutes of his stuff. I always forget what his device is called, but it's this this really cool Super Nintendo device. You might have seen it. I gotta pull this up. I always forget the name of this, because it's been through a couple of iterations as well. It's called, is it the 21FX? In this case, the top loader. And I believe he has some demos of it as well. I wanna share some of his picture links on Twitter, because these are just really cool. He's laughing at me, but it's really awesome. 21FX. So I'm just linking some pictures here. Sorry, we're raiding your Twitter on the stream, man. But where's the other pictures? Some just beautiful board shots. Oh, I love it. Where's my image location? I'll just copy the tweet. So that's Thrash HT. So what does it do? It's basically a man in the middle thing between like a SNES cartridge and the SNES itself. It allows you to do things like basically pause the game, get save states. I don't know if it gets save states, but definitely like you can inject stuff into the memory, things like that. Basically just like the ultimate SNES debugging tool, and I really want one. It's awesome. So that's really cool. SpaceCat64, nice to see you back, Ferris. First stream of yours I've been able to make it to since you got back. Yeah, cool. Good to see you. So yeah, I don't actually know what the 21FX does altogether, but I know that it's like a general like tool that you can use to manipulate the SNES while it's running. So you can do a lot of things that you would normally do in an emulator or a debugger, but it's actual hardware. So really cool stuff. I don't know what his plans for that are either. I just keep seeing stuff about that, so I had to share. So I did that stuff. I did stuff like refactor, some sync stuff, just fixing a couple other small bugs, that kind of thing. What else did I do? I did gamma. And this just does normal 2.2 gamma, which is correct for PC screens. It's probably not correct for these LEDs, but it does make the stuff look better. It makes it look a little bit brighter. Yeah, and then the rest of the stuff I did was all the speed changes. So I think that's everything I did in the last week. So it was actually quite a lot of progress. I'm pretty happy about that. Yeah, another thing that was also really slow. This was pretty interesting. It was the breakpoints and the watch points in the emulator. Let me bump this size up a little bit. So basically every cycle it would check if any of the watch points were hit, or well, this is actually any cycle that reads or writes to memory, and then every cycle would also trigger, watch points and here's the breakpoint stuff. Basically always checks if we're on a breakpoint between every instruction, and then every instruction that reads or writes to memory, it also checks the watch points. And the thing is that all I did was I added these length checks here. I noticed when I profiled this that it was spending a lot of time actually doing these lookups, this Hashmap lookup in this case and a hash set lookup in this case. I can't remember exactly, but basically doing these hash lookups. And I noticed it spent a lot of time doing that. And I went into, I explained this in the note here as well, but I went into the Rust source code actually. If you go to, if I search for like RustVec, then we have the source up here. And I could actually look at that. In particular, I did that, of course, for like Hashmap and stuff. But I found that it wasn't doing, wasn't earlying out if these collections were empty. So it was actually always doing the hash, and it was always doing some of the lookup routines, which is probably fine for a default implementation, but was really slow in this case. So all you have to do is just check if these are empty before actually trying to look up the hash. So that was another thing that saved some cycles. And yeah, then I did like the logging stuff and the rest of the stuff that I changed. I also went through, and I did a little bit of this in the last stream, but I went through and I removed all of the different read word and write word instructions, or like all the memory mapping stuff that dealt with that, because like the system only has a 16-bit bus. So I basically removed all the word stuff and just did the 16-bit stuff instead. That was just a simplification. And then eventually we are where we are today. So that was a lot of stuff. Diff params talking more about the general hardware debugger. Original purpose was for SNES cart dumping for Bu. Bu, by the way, is the guy behind like Keygon, used to be called BSNES, and hardware testing for preservation, which is really, really cool. I totally want one for making more demos. That'd be really nice. Yeah, so the current version through the expansion port is complete, and Bu is using it to dump his entire SFC ROM set, which is just fantastic. Bu does amazing work. Not only is the emulator like the SNES emulator, but also he does amazing work in terms of SNES preservation and actually, you know, buying up carts, doing scans, doing ROM dumps, just to really make sure none of this ends up disappearing in obscurity, which is absolutely fantastic. So that's really, really cool. So yeah, Diff params hardware helps with that. It's just so sexy. So that is where we are today. Whew, an hour and a half to explain all that. I wish I could have done it in an hour and a half, and in an hour and a half. Anyway, so where I'm at basically now is that a lot of games are working. The emulator is a lot faster. There's still a bunch of stuff that isn't working. In particular, I still haven't done the bitstring ops, and there's a lot of games that still use those. So I need to do that as well. But as far as like the video, like the hardware that I've implemented, as far as that's concerned, a lot of it's quite correct. I'm still not doing gamepad interrupts, but I don't think any commercial game actually uses those. Again, there's a couple bugs, like there's the disappearing lasers and Space Invaders. I can actually show you these bugs, because at least one of these I want to work on today. Or probably not one of these, because I just don't know what it is yet, and I'd rather have more screen real estate while I'm doing that debugging. But if we look at, for example, vertical force. Diff param also said that Bu found some byte errors and ROM dumps from the 90s, which is just awesome. Not awesome that there were byte errors, but it's really cool that someone's actually able to go and check that stuff out. Let me rebuild this again without the logging, because that was really slow. But yeah, I wanna track down some of these bugs, and I also ran some homebrew ROMs, which the games are, well, so there's a couple of them that they appear to just run really poorly, and it's not actually a performance problem, even though it looks like it. It's actually there's an issue with how some of the registers are implemented. And I did a little bit of research, and I think I know why. So this is one of the bugs, by the way, that these enemies, or I think these are actually both power-ups, they only do half their cycle. I think some of these will also disappear, some of these other enemies. So that's basically like the first bug that I know about that I just don't know what it is right now. I don't want to sit here and play this and get to the first boss because it actually takes a bit. And then the other one is I'll run Space Invaders. Again, this one has this really cool animation in the beginning, which if you get a lot of the display timing, like if the display timing and the drawing timing are out of sync, this just totally doesn't work. So I'll just skip some menus here. And eventually we'll get into the game. And the problem is, so there's me. None of my lasers show up. And the enemy lasers don't show up until they're like past this row here. And I don't know what that is. I've debugged some stuff to try and figure it out, but I'm just not really sure. So I have to do more debugging there. That's one of the known issues. Also still haven't done sound, of course, which I want to do. Another one of the issues is, again, I'll pull up one of these homebrew ROMs. And in particular, I want to pull up the one called Super Bounce. Now, this game isn't the coolest game around, but it's very helpful in this context. As you can see, this fades in super slowly, right? It looks like it's just running really badly, but it's totally not. And so I'm pretty sure I did a bit of debugging on this yesterday, and I'm pretty sure I know what it is. So one of the nice things about this is because it's homebrew, I actually have the code. So if we go down here to Super Bounce, I can pull some of this up. In particular, we'll go to, where is main? Oh, it's just superbounce.c, I guess. So the first thing that we'll find the main function here is just can see how some of this code looks. Which is up here. Make a bunch of variables on the stack. Set a bunch of data in the wave data, which I'm guessing is the data for the first wavetable in the audio stuff. Then it turns the display on, which basically just sets a bunch of registers. It's not that important. Then it calls this PVB adjustment thing. PVB is Planet Virtual Boy, I'm assuming, which is because that's the screen that actually shows up when it's doing that. It's this screen. So what this function does, it copies the background data into where it needs to go to display this screen. Then it sets up the world data to actually, so the hardware will actually display this data. And then it will fade the logo in, and then it will wait for basically any gamepad key to be pressed or button to be pressed. And then it will fade out. So like if I push any key here, then this will fade out. I think I actually have to hold it. So no, it actually did work. And then it fades out just super slowly. So if we look at what this is actually doing, let me just run this again because I actually don't want it to go in the game. If we look at what the code's actually doing, so it sets this brightness variable to 0, and it says while it's not 32, it will do 40 cycles of reading the XP-STTS's drawing status, whatever status. So it's reading the status of the drawing registers and then waiting for it to change. That's all it does. It does that 40 times, and then it will output the brightness to the registers and then increment the brightness. So altogether, it runs this many times. And what's actually happening is this drawing status register is not changing fast enough. So if we look at the bits of that register, let me pull up the text scroll again. Because it's just so good. 1 second. You just keep this stuff open. Okay. If we go into the VIP and we go into the, I know it's the display or the drawing status. Or, no, sorry, XP is drawing status. DP is display status. So it's the, so it's this register in particular. And if we, so that's 5F840. We can look at the code as well and verify that. We go into the, so in this case, it looks up the VIP regs with this offset. If we go into libgccvb, which I guess is dogp's gccvb header. We have VIP regs, which start at 5F800, which we can see is this, and then we just need offset 40 hex. And if we look at XPSCTS, this is actually 20 hex, but this is a pointer to a bunch of half words, which are shorts. So you can multiply this by 2 and find the actual address. So that's definitely what this is looking at. And if we look at the actual bits, we have a bit for whether or not the drawing's enabled. We have different bits so that when the drawing hardware is actually doing its drawing, whether or not it's writing to either of the different frame buffers. And this is not left and right frame buffers, by the way. This is if it's writing to both the left and right frame buffers, but for frame buffer 0 or for frame buffer 1. And those are the two, like, basically back and front buffers. They swap each frame, or each game frame, which is, I don't need to explain that. We have another bit that says drawing exceeds frame period. And so it's possible to set up the parameters to the drawing hardware such that it will take longer than a game frame, so longer than the time that it would need, or that basically longer than the time between different drawings, like drawing procedures. So basically overflows the amount of time that it has. When that happens, it will delay the next game frame and it will raise this bit. You can also get an interrupt with that as well. And with the way that I'm emulating the video hardware, this like just never fires. Like I think I just have it set to like 10 milliseconds that it always takes to draw. And that seems to be fine for all the games I'm testing with. And yeah, so this never fires. I don't think we have to worry about that. These last bits, though, are something that I'm not implementing. By the way, I'm pretty sure that these ones here I've actually done correctly, because like one of these is going to be 1 as long as you're drawing, and it just depends on which frame buffer you're using, which one will be 1. And then this is 1 as long as the drawing is enabled, not necessarily the drawings happen, but as long as it's enabled. So those are generally pretty easy to implement. And so if we look at the code, by the way, this is waiting for that register to change 40 times, right? But this will only change, I think it's like 1 or 2 times per frame, right? And so then that makes this loop of 40 here actually take quite a while. This will take basically 50 frames a second. This will take like, I think like 75% of a second or something, like 0.75 of a second per iteration of this, and then multiply that by 32 and you get, quite a long fade up. So this would actually make sense that that's what's going wrong here. So it's either these are wrong, but I don't think they are. And there's a lot of other games that rely on this that totally work. Pretty sure I got those right. But then these ones are fairly interesting. So the current Y position. So this is fairly interesting. We can just read the documentation that's here. Current Y position indicates which pixels are being rendered by the VIP within the current column of pixels. Pixels are processed in units of 8, so multiply this value by 8 for the actual vertical coordinate within the frame buffer. So what it's basically saying, and by the way, I actually think some of this is wrong, and I'll explain why in a second, but basically it's saying that the video hardware will process all the video in blocks of like 8 pixels tall blocks. This is saying it will do that per vertical scan line. Remember that the scanner is actually sideways on this hardware because it scans right to left. That's more convenient for actually sending that data to the LEDs. So basically, this is claiming that it will process 8 pixels at a time vertically for every scan line. I don't think that's correct, because I'll explain the other bits first, and then I'll explain why I don't think that's correct. But it's also saying that these actual bits here are that value divided by 8, which would make sense because it's just like offset in 8 pixel blocks. So that's what you actually set for this. So this should return that value as it's drawing those different bits, like wherever it's drawing. And then you have this drawing at Y position bit, and that's here. There's the drawing control, and you can set a Y position here. And basically whenever this value matches this value, you'll get this bit set for a certain number of microseconds. I think it's like 56 microseconds. And I don't think that's listed here, but I don't remember. Might be in some other parts of this document. So the reason why I think that's wrong, what I think is wrong about it is I don't think it's happening per column. I don't think that makes sense. Because if it happened per column, then you could get, this would change. I think, so we could just do a little like napkin math here. So it's 224 pixels high, right? Divided by 8. So this would happen 28 times, like 28 vertical blocks. But if that were per scan line, then this would happen 10,000 times per frame. And remember that loop was sitting there counting to 40 different changes. And that's 40 by 32 that it was doing, because it was doing 32 brightness levels waiting for 40. So this is 1/10. You kind of see the problem here. Like there's, like that would make the register change way too many times for what that loop expects. And I know that this game runs on the hardware, so that can't be right. So my guess is that the video hardware, instead of like processing 8 pixels per column like that, I think it's actually processing 8 pixels for the whole scan line, or for the whole screen. So we'll do 8 column high or 8 pixel high rows, and it will do like 28 of those. Because then we're at least in the ballpark of the kind of numbers that wait loop expects, to actually make this, decently fast. Because then it should only take like a second or two. Because we're around 30 there, which is around 32, and then 40 of those is about a frame. So that actually starts to make sense if that's the case. I have a little bit more evidence of that I can't remember if it's in this piece of documentation or in a different piece of documentation. What was it? Yeah, that there's actually a hardware bug. Need to find the right register. This is one of the ones I actually implemented on purpose, because it's kind of a funny bug, and it's a very easy one to implement. And there is a game that this shows up in, at least, so I can show you that as well. Just want to try and find the particular register. Clear color. This register. So I don't think it's listed in this documentation, but it's listed in another piece of documentation. But the thing is, so this clear color is basically, there's these last 2 bits that are used, because it's 2 bits per pixel. And for every like block of pixels that it will process, it will fill the whole thing with this value first. And then it will draw all the window data and all the object data on top of that. And one of the weird quirks that is documented here, or not in this piece of documentation, but another one, is that if you change this register, that first 8 pixel high chunk will still use the value from the previous frame. And the fact that it does that vertically, like if it did that, I could understand that kind of bug if it happened the very first 8 pixels if we were processing per column, because like that, the nature of that kind of problem is basically that the new value isn't latched until too late, until we're already drawing some stuff. So I'm guessing it latches that value after it writes out a chunk of 8 pixels, which is why it would happen after that first row. So if we were processing by column, then that should only mess up the first 8 pixels of the first column, and then it should be fine after that, right? But the fact that it covers the whole screen is also kind of another clue that that's not really how this hardware works. So that's what I'm guessing. I can also reveal that I did a tiny bit of cheating as well, and I looked at Mednafen yesterday, and that's totally how they're doing it. So, so that's probably correct. I can also show you the game where this shows up in. It'll be kind of quick though, so we gotta watch carefully. So this is SD Gundam Dimension War. And so this should fade in like a logo. And I want you to watch the top of the screen here, right? Because the screen's going to flash. It's going to flash to white. Here it comes right there. You see that? See how it's kind of glitchy as that's changing? I'll show you again. But this is that bug in action. And if you play this on the real hardware, or if you go and like watch some long play of this on YouTube, you'll see that that bug's definitely present. So it's a problem with the game itself. There it goes. So that to me just says that I don't think that the video hardware is actually processing per column. I think it's doing these blocks of the full width of the screen by 8 pixels high. And that puts all the numbers that we need kind of ballpark where they need to be. So I think the next thing I want to do is try and implement those registers. So what that means in terms of implementing that is that I need to split up the drawing routine so that it can actually draw just like a big block like that, a big block of 8 pixel, one 8 pixel high chunk at a time. This also means that it would actually iterate through all the windows and all the objects and everything and then clip those against that block basically for each one of those blocks. But I think that's fine. I've also read other places that there's evidence that the video hardware doesn't work how it's documented a little bit, and that kind of is what I hear in that's probably what they're talking about. Again, this is one of those things about this hardware that that there actually hasn't been that much work. Like people just haven't done that much work on this in terms of like accurately trying to find out what the hardware is really doing at that low level. So there isn't much we can do about that other than kind of punt right now. So that's what we're going to do. But yeah, so I need to change the drawing routine so that it will do those 8 pixel high blocks. The other thing that I need to do is I need to actually make those take some time and yield. Like right now what I do is, let me pull up the code. In the VIP, I have up here that there's a display frame quarter period. So I refactored all the timing just in like the state changes for like when it changes between different like display and drawing states. And I basically split the frame. So the frame is 20 milliseconds, and I split it into these 5 millisecond chunks. And I can show you the code that actually does transitions on those, so you can see the different things. So you can basically think of this as a 12.5 hertz clock. Here. So when the video hardware is told that the CPU ran a certain number of cycles, we basically sit there for every cycle. We increase this display frame quarter clock counter. And when that goes above this quarter period, then what we're going to do is we're going to basically reset the counter, which I think happens down here somewhere. Oh, it's right here, actually. We basically display the counter, and then we do some transition. So we keep track of which quarter of the frame we're in, 0, 1, 2, or 3. The first one, all it basically does is fire off a new frame clock. It says like, okay, new frame starting. The second one, it will, the second and third quarters here I use for the display routine. And you'll notice I actually do the display. So this display function actually will go and output the pixel data from the frame buffers into the output pixel data for the emulator. So I do that at the beginning of this process. Just because it's basically arbitrary. If I'm going to do it all at once, I could do it at the beginning or at the end. Or I could simulate it happening in tandem with the CPU, but it's a lot simpler to just like fire it off here at the beginning. So I just do that really quick, and then I will start setting registers to basically transition the hardware into faking that it's like just sending the left frame buffer in the first or in that second quarter period, and then the third one I'll do the same thing with the right one. Also in this third quarter period, that's when I end the drawing status. So I say that this in the second and third periods of the 4 of the frame, we're doing the display process. Or sorry, the second and third we're doing the display process, and in the first and second we're doing the drawing process, and that tends to work pretty well. The last one basically just ends the display process, which is the last little state change we need. So basically what that means is that the left and the right frame buffer display periods are both 5 milliseconds, which more or less matches the documentation. The drawing period then is 10 milliseconds. And in this case, it's very easy to just like enable and disable that. And it only, again, it just draws at the end, I think. I think this end drawing process actually does the drawing. But it sets the right, register bits so that the CPU, like, it looks like it's actually doing drawing work to the CPU. And a lot of games, of course, are paying attention to this to actually find out, like, if they should update like LED brightnesses or update graphics data, that kind of thing. But the reason I bring all this up is because the other thing that I need to do is not just get the thing to draw in blocks. Like, that's trivial. I just, invert some loops, and yeah, that should be pretty easy. But the other thing I need to do is make it look to the CPU like it's actually doing this in these steps. So I basically need to divide that 10 millisecond period, which I might drop down to 5 seconds just to make this a little simpler. But I basically need to, divide that period up into some time that it would have taken to, like, in this first 20th of this period, it will be working on the first column and the second column and so forth. Also need to get the timing correct for the how long that match bit will stay high. And maybe I actually don't need to be that accurate with that, but yeah, need to kind of do those things. So I was hoping to kind of get to that today, but I ended up spending an hour and 45 minutes just talking about this stuff. And I don't want to run too late tonight, so I might actually just not do that on the stream right now, just because I think that it'll take me a bit longer than that. Although I could redo the drawing so that happens in blocks, just to do something on the stream. I feel like I'm just talking a lot. By the way, guys, if you have any questions or anything, just holler. If I'm not making sense or something, let me know. If you guys are lost, let me know. More than happy to explain what's going on in here. But currently, so I'm just kind of scrolling through the drawing code right now. And what it basically does is we figure out which frame buffer we're going to draw to. We write out the clear pixels for all those. Then we rewrite out this this first 8. This first block with the last frame's clear color. So that's emulating that bug. And then we just go through all the 32 windows and just draw those to the different frame buffers. Matrix404 says, will you do some demos for Rustual Boy? I'm genuinely considering it because I think this hardware is really interesting. Ironically, I don't know, something about it I find interesting. And there's decent development tools available. There's this GCC VB thing, which is a GCC fork with some patches that let it compile to the Rustual Boy CPU. And there's a couple helper libraries like we saw in that C code that, libgccvb has a lot of like these names for these registers and stuff already mapped. I'm sure it has some other things as well. I haven't really looked at what else it has. Actually, if it's header only, that's kind of cool. Don't really know what any of this stuff is doing. Thinking about doing that. Although I would need to find something that I haven't seen done before, or something to be able to use like this hardware in an interesting way, and not just do like some thing that looks like an Amiga demo from the 90s, which is kind of cool in its own way. But I want to figure something out. Diffpram, hey Ferris, how many official released carts were there for Rustual Boy? Also, do carts have unique mappers and coprocessors? So I'll answer the second half. Basically, no. I don't think any of them had coprocessors. I don't think any of them had mappers either. There's 16 megabytes reserved in the address space because this is a 32-bit system. There's 16 megs worth of that's just dedicated to cart ROM, and I don't think any of the ROMs got bigger than like 2 or 4 megs. They were all pretty small. So I think it was just straight up ROM chips. And I found the data sheet for some of those. So need to actually need to send those to you. And then the first question was, how many official release carts were there? There were like 16 or something. Let me, I think Planet VB has all this info. This is a really nice site in terms of preserving all this information. So this is all the released games. You can see some of them are Japan only, some of them are US only. Not that many. Daniel Collin, have you considered getting it working on a real VR headset? Yes. And 3D TVs. I don't really know what it takes to do that, though, but I actually totally want to do that. Because, like, some of these games are quite playable. Another thing that I did is I bought a couple teensies, and I want to do... I want to do a controller adapter, because the controller, other than some... The controller is basically an ADC and a shift register. The shift register to read all the buttons serially, and then the ADC to tell you if the battery's low or not. So it should be pretty easy to build a small adapter for that. I ordered a couple dead Virtual Boys and some donor carts as well that I'm going to tear apart and do that stuff with. I guess I don't need the donor carts for that, but working on something else. Or thinking about working on something else. So yeah, there are not a lot of games. I love too, like, the little details in this site. Like, they have this picture of this cart, which I believe is from the patent for the cartridge. And all the cartridges have this stupid proprietary connector on them, which, as you can see, maybe you can't see that, but it's like a bunch of little holes, and then there's pins that stick out of the cartridge slot inside the unit. It's really similar to, I don't know what it's called, but like the small laptop drives now. The connector that's on there is very similar, except I think the hard drive connector has both more pins. I think it's a little longer, and I also think that the pins are too wide, if I remember reading that correctly. So they're not actually compatible, which is annoying, because those connectors are really easy to find, but the Virtual Boy ones, you just have to tear apart carts if you're going to do anything with that. So that's fun. But yeah, to actually kind of invert all this code and then make it do the drawing in blocks, basically have to like just go through all these windows per block and basically do what they're already doing, but clipping on those bounds. So it'll be a lot of extra like sprite processing, but that should be fine, because most of the clipping can be done beforehand. It's the timing that'll be a little bit annoying. Ep.014 looks kind of like an IDE connector. I think the pins are still too big. Like, I think is that mini IDE? Is that what that's called? I actually just don't know because it is the smaller laptops. That's the right size. The older IDE, it's not that big. The carts are actually, like, compared to my phone, it's like that big. So it's a pretty small edge connector. And they're very thin as well. I'm honestly sad there's not more games for this, just because it's a couple of them are pretty cool, and like they demoed some like Star Fox stuff with it that just never came out. There's some homebrew stuff though that's worth checking out. Quite a bit of homebrew, actually. Well, I mean, compared to the release games list, at least. Again, it's all on this Planet VB site, which is really cool. Want to do that stuff. Yeah. Ep.014 says if you have to scroll, it's quite a bit. Yeah. At least compared to the official ones, for sure. Because that's just a bit sad, And Nintendo just like does not want to have anything to do with the system anymore. Because it was a commercial failure, and it's I mean, it was never meant to be like. It's fairly interesting because it's the same designer as the Game Boy. I think I talked a little bit about this in the last stream, and you see a lot of similarities, like the fact that it totally just draws 2D stuff and that it's only 4 colors. But yeah, the black and red just looked dated at the time, and it had a ton of warning labels all over it about how it can cause eye strain, especially for children under 7. So like, no parents bought this for their kids. It was totally antisocial. There's a link cable port and there's a link cable plan, but I don't think any of the games actually used it, and the link cable never came out. So it was just not great, and apparently that's pretty understandable because I think it was rushed to market, because I believe this was in that window between when the original PlayStation and the N64 came out, and was it the president of Nintendo at the time really wanted to have another console release to fill that gap and remain in people's minds before the N64 came out, so he rushed this. I think they sold 800,000 units, which is still not terrible, but considering a lot of them ended up just like on store shelves for like $20 a pop by the end of like a year later, not that great. So that's fun. But yeah, it's getting a bit late, so I think I'm going to stop the stream at 22. So you guys have any other questions or anything, fire away. Otherwise, I can shut it off a little bit early for the people that are going to binge watch this later. Also, I'm thinking about just continuing to work on this project basically until, it'll probably be another couple weeks, because I want to do audio. I want to do some of that top level stuff, like making this work on VR, even though I don't really have any headsets, so I might need someone's help with that. There's a couple other things like setting options that I really want to do. Different scale options, that kind of stuff. Daniel Colin, have you tried some of the demos on the site in the emulator? Yeah, I tried a couple of them. I tried the demo for the View Debugger, for example, and I tried, again, those homebrew ROMs. And they appeared to work. Let me find that View demo. So the View Debugger was the like official debugger, hardware debugger for the system. Yeah, it's the sample software for the View Debugger. I tried this, and I actually don't think some of it runs correctly, but I'm not sure because I don't really know what this is supposed to do. So this is like an affine mode demo apparently, and if you press some of the buttons, it'll like change some of the parameters. But you very quickly run into parameters that are kind of useless, and it starts out with not very good parameters. So I'm not really sure what's up with that. And if you just hit like start, or I think it's other buttons like A, it'll just go between these different modes. This is a demo for the line shift mode. I don't think this one can be interacted with. I haven't tried any of the homebrew demos though. Oh yeah, okay, so when this says demos, it actually means like these store demos. For homebrew, looks like here's Game of Life. You can try that. What else was there? Some sound demos, water ripple, Mario flying demo. I kind of want to try Game of Life. 4 pixel tiles, 8 pixel tiles. We'll do 4 pixels. Actually, we'll do direct screen draw. That one sounds the most interesting as far as an emulator test. Let me go ahead and grab this. Hashmap says no questions so far, just letting it all sink in. That's cool, man. Probably a lot to take in. I'm not good at not talking a lot on these streams, but I guess that's why you guys watch. So this is supposed to be Game of Life with direct screen draw. And other than the fact that it is totally slow, it's working. Looks like it's working at least. Interesting. It's not using like any CPU. Let me do a logging build and see if there's anything interesting in there. So this is actually pretty cool. Let me show you some of the output I'm getting from this, because there might actually be something interesting going on here. It's reading byte from cartridge expansion, which sounds wrong. So maybe this and the other games I saw reading from cartridge expansions, maybe that's actually a bug somewhere. I might want to disassemble this actually and try and find that out, because it might explain some of the other bugs I described earlier. So that's actually pretty interesting. Also, you can see we have these start display. Yeah, so we have a frame clock rising edge and a game clock rising edge. So the frame clock happens every 20 milliseconds. And that's just, going to output whatever's in the frame buffers to the LEDs. The game clock is basically how many frames happen. It's like X frames between when the frame buffers swap. So a game like this, or a cartridge like this, is definitely going to, if it's actually going to be doing direct screen draw, it's definitely going to be, spending a lot of time. So in this case, we're getting a game clock, and we get, here's a starting display process and the end of the display process, and we had a frame duration of 5 milliseconds. And then it happens again. Okay, actually, in this case, the game clock is the same as the frame clock. So never mind. I was expecting to see a few frame clocks per game clock in this case, but I guess that's not what's happening. It might also be that this just does run this slowly. I don't really know. But it seems weird that it's reading from these weird addresses, so I might have to look at the code, which it did come with, and start, digging into that. Because if this is supposed to be aligned with the screen or something, and it's not, oh, this is nice and short too, so this will actually be a really good debugging case. If it is the case that, sorry, I'm getting a little tired now. If it is the case that those reads in the weird cartridge expansion thing are wrong, then that's actually a thing I would love to fix. So I think I need to dig into that. But other than that, though, it looks like the output from the Game of Life simulation itself is relatively correct. Although it's a bit asymmetrical. I'm not really sure why that is. Also, there's this big chunk on the left here that's just not rendering to. I'm wondering why that is. So that'll be interesting to look into. But I don't think I'll do that right now. Oh, also this says the width is 192 and the height is 112, pixel size of 2. Okay, so the scale at least of these is definitely correct, because I have the emulator window scaled x2, I believe. So these are going to be basically 4x4 pixels, and that looks about right on this screen. So that's probably correct. And this setup, I guess if it had a bunch of X-looking things on the left and then a couple lines on the right, that's probably correct for what we saw there. Although it is a bit offset still. Just gonna restart this. So that does actually look like the setup we have, of course shifted. I'm guessing that's what this table is. So generally this looks pretty correct. But yeah, those weird memory reads are interesting. It's also running really slowly, which I wouldn't have expected, but that might just be how it is. So I'll have to dig into that. But anyway, I think I'm going to cut off the stream for today. So thanks again, guys, for tuning in. Hope you are enjoying the new time slot. It turned out to work really well for me today, which is, last week was obvious because I had work off and I didn't have to worry about it. But today was pretty good. Yeah, pretty easy to get off work a couple hours ago, eat, hang out, and then do this. So it's pretty chill. I don't plan on trying to go that late when I do these every week, because that is the goal, is to do this every week. I probably won't go that late, but if it's anything like today, I'll have plenty to talk about and I'll have plenty to go over. So at least that'll still be interesting. Server Earl says no. Yeah, sorry, man. Gotta sleep. I just arrived. Yeah, sorry about that. Dana Colin, thanks for a great stream. Yeah, thanks for watching. This is I really enjoy doing this because it's it's just super fun to talk about this stuff. Like I'm basically working on this stuff anyway, so it's really fun to share, and yeah, make a thing of it. So I really enjoy that people enjoy this. So for the first time I caught you live, next week, 2 hours earlier. that should help. 8 p.m. CET every Thursday. That's my goal. Server else is the best code is written at night. I totally agree. I guess that's the only downside about a Thursday evening slot is I'm definitely not going to want to go that terribly late. I'll probably want to go a little bit later than today, but I'm just pretty tired. So we'll see what happens. Anyway, thanks again, guys. I'm going to head out, and I'll see you next week. By the way, feel free to bug me on Twitter or whatever. Server says CET, that's Central European time. I'm located in Oslo these days. But yeah, feel free to bug me on Twitter, bug me on Twitch, bug me wherever you can find me, really. Be happy to share more of this stuff. Reddit as well. I'll upload this video as soon as I can. So I'll probably have it up and post it either tomorrow morning or later today, depending on how long it takes. So yeah, thanks again, guys, and I'll see you later.